Hey everyone, I'm Anibal, the former project sub-lead of WESP at WARR Rocketry and the simulations team lead. Today, I'm excited to share our team's work on Whisper, WESP simulation predictive rocketry tool. But before we jump into how we developed this trajectory simulator, let's first talk about WESP. WESP was founded in May 2023 and has since grown to over 40 active members, putting in more than 25,000 hours of engineering. In 2023, WARR launched the X3, Project Cryosphere's hybrid rocket with over 2,248 pounds force of thrust. Then, in April 2024, WESP completed its maiden flight with EX-1D. We then followed it by our trip to the US in June of that year to compete in the Spaceport America Cup Challenge 2024. There, we launched Europe's and WARR Rocketry's first ever stage student-built rocket. On April 21st, we launched EX-1D, our first single-stage rocket from Straubing, Germany. The primary objective was to validate our recovery system at high descent speeds exceeding over 200 feet per second, and the mission provided crucial data for our future development of our multi-stage rocket design. Then came EX-1E, our rocket to be used for Spaceport America 2024. The apogee target calculated by Whisper for it was approximately 27,300 feet. We would participate in the 30,000 feet COTS category, and we would carry a payload developed by WARR Space Labs with the experience that they gained with ISS experiments. Some key innovations that we presented with the rocket was the SRAD carbon fiber airframe that we wound by ourselves, the live telemetry, some additively manufactured titanium motor mounts, and Whisper. Whisper is our in-house software for simulating 6 degrees of freedom rocket trajectories. The team developing it consists of over 8 active members and a total of 14 developers. Our approach focuses on rapid iterations and parallel progress, with having weekly meetings for updates and feedback. Originally, Whisper was built for solid propellant rockets since WESP primarily used solid motors. But as the project evolved and the team grew, we expanded its capabilities beyond solid motors, allowing for liquid and hybrid motors too. We built Whisper to overcome the limitations of OpenRocket. While OpenRocket is great for subsonic flights and single-stage rockets, it operates under simplifying assumptions. For example, having low angles of attack and basic aerodynamic models like a flat plate fin and so on. That makes it less reliable for supersonic simulations and multi-stage configurations, which was our idea of a rocket. Whisper addresses these issues by offering a set of features like a dynamic mass 6 degrees of freedom trajectory simulator, real flight data corrective factors for supersonic regimes implemented, safety range analysis, a user-friendly web app with 3D trajectory visualizations, and an automatic safety report generation. To calculate the equations of motion, we initially considered Keynes' equation for an arbitrary particle, but we found out that it required tracking all internal and external particles. So instead, we used Reynolds' transport theorem to model the motion for any variable mass system. This gave us the translational and rotational motion equations, where you could integrate the dynamic mass evolution due to propellant consumption, and the rotational motion was derived similarly. These equations have 3 key components and 3 parts: the kinematics of the rigid body, the Coriolis effect, and the effect of thrust. Essentially, if no gas leaves the nozzle, if the velocity is 0, the equations simplify to rigid body motion, which confirmed us that the models were valid. To efficiently compute these equations, we reformulated the equations into a state space representation. The state vector includes the position, the velocity, quaternions for the attitude, and angular velocity. We evaluated different integration methods, comparing Runge-Kutta and El-Soda, because the system is complex and dynamic, so we needed a robust and efficient integrator. El-Soda dynamically adjusts step size and method, which makes it ideal for our needs. Even though it's a bit more computationally expensive than Runge-Kutta 45, um, it's something that is not time critical, as you can leave the simulations running overnight, or we're talking about a difference of maybe 30 seconds in computation, which is, for these applications, not critical. Some corrective factors have been derived from DATCOM, and these are essential for any kind of simulation in supersonic regimes, where you're flying at Mach over 1.5. These basic equations that were presented by OpenRocket and the other simulators use, they break down due to the simplifying assumptions that they work on. DACOM provides a very vast database of real flight data with over 3,000 pages that have now been digitalized by the team, allowing us to interpolate aerodynamic coefficients for better accuracy, these being the lift, drag, normal force, and so on. Some examples include the coefficient of normal force for an ogive nose cone, which factors in compressibility and slenderness ratio. Similar interpolations apply to the center of pressure calculations for the afterbody and the normal force coefficient for fins, and so on for all aerodynamic surfaces. But to make it accessible and usable for non-programmers, we wanted WSPR to be user-friendly, so we developed a graphical user interface. Initially, we went over several iterations, but we used a Python-based frontend. But later, we migrated to a Vue.js web application for better performance and usability. The web app allows users to configure multiple rocket stages, motors, airframes, aerodynamics, and environmental parameters. In the future, we have the objective to host this backend simulations on TUM's LRZ supercomputer for a global web-based access. At WARR Rocketry, we don't take safety as a joke. It is of our utmost priority to have this as our number one thing to work upon. So it was natural for us to develop a safety range analysis to optimize design and quantify any kind of uncertainties that there were. Uncertainties come in all shapes and forms, like the rocket inertia, any fin misalignment when you manufacture it, the motor performance, the surface roughness, and even the weather conditions. To do so, we use Monte Carlo methods that we run over thousands of simulations that you can leave overnight to prepare for launch day with the latest weather forecast for that day. The results on the figure right next to me compare OpenRocket, WSPR, and actual flight data for apogee and landing calculations. Weather is the most unpredictable launch parameter, so accurate forecasting for weather is the most crucial out of all uncertainties. To do so, we relied on Windy, which provides several models, such as the ECMWF and GFS, which is the American equivalent, with global coverage and up to 10-day predictions. We chose ECMWF because it was the most accurate. It has a better spatial resolution and a more frequent updates. Then the simulated trajectories can be visualized in 3D with our feature of augmented reality scenery. These trajectories are exported in a GIS-compatible KMZ format, including speed and altitude data. We're working on integrating this feature into the graphical user interface so that non-programmers can use it too. And after every simulation, an automatic report is generated. These reports include launch crew details, the rocket specs, a summary of launch critical results, and a go no go decision to make launch day preparations and decision making for safety officers a lot easier. But Whisper does not stop at simulations. We also use it for post flight telemetry analysis. We validated our results using a Blue Raven telemetry data for the EX-1D launch at Straubing, Germany. It was a stress test, and we analyzed this using Whisper. And one key finding that we got out of it was that the main parachute deployment induced a voltage spike, unintentionally triggering drogue deployment as well. But as it was a non-nominal case, EX-1D served as a great test case for validating the simulations and also the rocket itself. Because safety is our top priority, we conducted a comprehensive safety range analysis for Spaceport America Cup 2. The analysis considered all tolerances that I mentioned previously, especially weather forecast with wind conditions, because a sandstorm was due. The final comparison between Open Rocket, Whisper, and the actual landing point demonstrated Whisper's high accuracy in comparison with Open Rocket. In the near future, we have several key milestones ahead. The upcoming launches to Bremen in Germany and Spaceport America Cup 25 will provide further validation for our physics models. We're integrating DATCOM corrective factors to refine aerodynamic modeling, especially in supersonic regimes. And we'll continue improving Whisper and hopefully fully integrating it into Rocket, which is WARR's in-house design phase software for liquid propulsion system development. Rocket is a sister project that we have developed for small-scale liquid propellant sounding rockets. It allows us to simulate thousands of rockets configurations simultaneously and evaluating over 86 components across 5 major subsystems: fluids, propulsion, structures, electronics, and recovery. We used Rocket for EX4's preliminary design, which iterated over 70,000 different configurations, and this work has led to the design of 3 liquid propulsion systems. Kara, which was the first one, successfully hot-fired multiple times and was planned to being used for Spaceport America Cup 23. Rhoda, which was the one illustrated in the image right here, and Brunhilde, which was the latest iteration, which flew on EX4B as part of Project Nixus at EUROC 2024. Thank you for your time. I hope this gave you valuable insights, and I'd love to hear your thoughts or answer any questions you might have.